So today's lesson, Unit 1, Lesson 8, Motion in 2 Dimensions, and we're going to go over slowly how to add vectors in 2 dimensions using components. So first, let me explain what a component is. So up until now, we've looked at one-dimensional vectors, and those vectors would either be left and right, or up and down. And they could be different lengths, and we added them together. And how we added them was we would, for example, take this vector and make it negative so that it's actually pointing in the other direction. Okay? If this vector is A, this vector is negative A. And then we were able to add them because they were in the same direction. Adding vectors in 2 dimensions, a little more tricky. So how would I add this vector and this vector? I cannot get this vector to look like this vector. If I make this vector negative, if this is B, and I make it negative, it's like this. That's negative B. It's not in the same direction as, let's call this C. It's not in the same direction as C. So adding them, what we're going to be doing is we are going to split things into components. Because if you have everything in either right or left and everything either up or down, what we can do is we would take this, let's take B, and if we were to add C, we would take B, and then take, we call this the tip of the vector, and this the tail of the vector. So we take the tip of vector B and connect it to the tail of vector C. And this is where we started, this is where we finished. So if we connect our starting points with our ending points like this, that would be vector B plus C. And you would have to solve the triangle, right? You would have to figure out what this angle is, so you know what direction the vector is. And you'd have to figure out the length of that vector, so you know the magnitude of that vector. So yeah, good question. Why would we measure this angle and not say this angle? Let me call that one phi. Okay, and what you have to think about what you're doing is if you have your compass coordinate system, which I drew up there, but I'll draw it again here, where this is north and this is east, what you want to do is translate this vector. You want to move it, but you want to keep the length and the direction the same, and you want to put its tail at the origin of your coordinate system, like this. So that would be the same vector, B plus C, with the origin at its coordinate system. And therefore, to write what direction it's going in, it's either going north, some degrees theta, to the east, or you could figure out what this angle is, which would be east some degrees north. So looking at this triangle, you can imagine almost that your origin, which was here, to be here, right at the tail. And if this is straight up, then you know that that angle is the one you want, because that's north, and this would be east, so that's the angle you're looking for. Okay, but this is all easy to do if our vectors are up, down, and left, right. You can just connect them together, and you have a nice right-angled triangle where you can use SOHCAHTOA, your trig ratios, and you can use Pythagorean theorem. However, the question becomes a little bit more challenging if I wanted to add this vector, let's call it E, to this vector, let's call it F. And, I don't know, I also want to add this vector, let's call it G. Now, if you kind of connect the tip to the tail and the tip to the tail, then E plus F plus G all equal this vector. This would be E plus F plus G. And now you look at that and you say, where's my right angle triangle? I cannot use SOHCAHTOA. Like, what is that? What shape is that? That's some weird quadrilateral that I can't make sense of. And so what we're going to do is we're going to use components. So let me go back and explain what a component is, because that's the very important part. If you were to take any vector, okay, I have it written down here, but let's take this vector A. I can split it up into parts. So you're breaking one vector into parts. Now when you do that, you can break it up into as many parts as you want. But it makes sense to split it up into two parts, specifically where one part is perfectly parallel to your x-axis, and the other part is perfectly parallel to your y-axis. So here I have vector A, and here I have what we call the components of A. This is the x component, so I have a little subscript x, and this is the y component where I have a little subscript y. And in this, you can say that vector A, right here, is equal to its x component plus its y component. And this idea of components is going to really help us add all of those vectors, E, F, G, H, I, J, K, whatever. Okay, so let me pause there. Okay, so now that we know what a component is, let's go back to this problem. How could I figure out what this red vector is, E plus F plus G? And let me just give you a little overview of what we're going to be doing. And then we're going to do a problem, step by step, slowly. So each of these vectors, E, F, G, I can break them all up into their x and their y component. Or you can think of it as their horizontal and their vertical components. Same with F, I can split it up. And the same with G, I can split it as well, like this. Now when I do that, what you might notice, and if you don't, that's okay, you might notice that if you look at all of the y components, like this one, and this one, and this one, if you were to add all those up and down directions, like we've done before, simply adding up and down, you perfectly get this, the y component for the vector you're looking for. And if you add all of these horizontal ones, so starting from here, going over here, and then going over there with F, and then coming back there with G, if you add all of your left and rights, you perfectly get your horizontal component for this vector you're looking for. And then once you have this vertical and that horizontal component, you once again have a nice right angle triangle where you know the two sides and you're looking for the hypotenuse and the direction. So that's what we're going to do today. But we're going to take it step by step. And I have steps for you written down right here, steps 1 to 9. And we're going to go through these steps to help us answer this question over here. So in this question, right, we have 1, 2, 3, 4 velocity vectors called v1, v2, v3, and v4. What we're going to do is draw x and y components for each of them, and we're going to add them all to figure out what the total velocity is. So if we were to add v1 plus v2 plus v3 plus v4, what vector would we get? Alright, so let's start. Step 1, draw a labeled coordinate system. Okay, we actually have that here. Here's our y and here's our x. Okay, but I might give you a question where I simply say v1 is 12 meters per second east, 35 degrees north. So I might not draw this for you. So if I don't draw it for you, then you would draw, there's your y, there's your x, and if you wanted to, you could even label this as north and east if we're using compass directions. Next step. Draw each vector with its tail at the origin of the coordinate system. So that I've done. Notice that each vector starts at the origin. Each one has its tail from the origin going outwards. Okay. Step 3. identify the angle that the vectors make with either the x or y axis of your coordinate systems. That's already drawn for you as well, the angles. And then draw those x and y components. So that we're going to have to do. All right, so let's look at V1. Here's an angle. And so I'm going to draw an x or a horizontal component here and a vertical component. I messed up. That's okay, you get the idea. Imagine that's vertical. And a vertical component there. Same with V2. Here's our x here and our y there. V3, same. I'll use a different color here. They're going to overlap. Here's our x, and there is our y. And then V4, again, change the color. This one is only in y, so we actually only have a y component. The x component is just 0. Okay, so we've drawn all of our x and y components for each vector. All right, next step. Use trigonometry to solve for the magnitudes of those components. All right, so how are we going to do that? Let's look at V1. Now this is a right-angled triangle. And we know the hypotenuse and this angle. So what we're going to use is our trig ratios, SOHCAHTOA, to figure out what our x component is and our y component. So if we look at cosine, cosine equals adjacent over hypotenuse. So that's going to help us solve for that adjacent horizontal component. So the cos of 35 equals adjacent, which I'm just going to write as V1x, divided by our horizontal, which is 12. Let me zoom in because it's a small space for me to write. Okay, so rearranging that, you can multiply both sides by 12, and you're going to get VIX, or V1, sorry, it's not I, V1x equals 12 times the cos of 35. Kind of going over my space here. You type that into your calculator and you'll get 9.8 meters per second. All right, our y component, let's go up here. So our y component, this one here, it is the opposite side to our angle. So if we look at SOHCAHTOA, sine can help us. So the sine of 35 equals that vertical component divided by the hypotenuse. So the sine of 35 equals our vertical component, I'll write it V1y, over the hypotenuse 12. So rearranging, multiply both sides by 12, we get VIY, our vertical component, is 12 sine 35, which equals 6.9. Okay, all right. Now notice our x and y components do have directions. So our direction for x here is to the east. So I'll just write east. And for our y component, that's towards the north. So north. Okay, that's important because your y component could be down, which would be south. Right? And so later when we add south and north, we just have to remember how we've added vectors in one dimension that are in opposite directions. And we'll get to that. First, let's go to V2. Now V2 is 20 meters per second. It's this vector here, so that's 20. This would be V2x, and this would be V2y. y. And that is, once again, a nice right angled triangle. So to solve for our x component, again, we can use cosine. So the cos of 10 equals v2x over hypotenuse, which is 20. So rearranging, v2x equals 20 times the cos of 10. I'm going to run out of room, so I'll just write it. 20 times the cos of 10 is 19.7 meters per second, and that is actually west, not east. Okay, and we can do the same thing for the y component. So the sine of 10 equals opposite over hypotenuse. So that's our v2y over 20. So if we rearrange to solve for v2y, that's just 20 times sine of 10, which is 3.5. And that is north. Okay, now for v3, notice they give us this angle. That's fine. I mean, I drew my x and y components here, but if I move my y component here, then it is perfectly fine for me to draw it like this as well. Okay, this is the same as that, and this is the same as that. I've just drawn a rectangle where opposite sides are equal. Now this gives me 30, so if I want, I could solve this triangle with 30, or I can solve this triangle with 60. Now if I solve the triangle with 60, notice that our horizontal component is once again cosine, like we've been using cos in x. But it's not always going to be cosine. It really depends what triangle you're solving. If you're solving for this triangle here, notice that our x component is opposite to the angle, so you would use sine. It doesn't really matter which I use. If I use cos of 60, that is the exact same thing as writing the sine of 30. Okay, you just need to be aware of which triangle and which angle you're using to solve for your components. Okay, and that will be our v3x divided by our hypotenuse, which is 5 meters per second. Rearranging, you would get 5 times the sine of 30, or 5 times the cos of 60, and you'll get v3x to be 2.5 meters per second, and that is going to be west, because we can see the direction there. Okay, we'd have to do the same thing for our y component. You can choose which angle you want to work with. Right? You can either do 30, and your y would be adjacent to that, and you'd use cos, or you can use 60, where your vertical component is opposite to that, and use sine. But again, it doesn't matter because the cos of 30 is the same as the sine of 60. If you don't believe me, you can punch those on your calculator. And that'll equal our y component for v3, v3y divided by 5. So rearranging, we'll get v3y to be 4.3 meters per second, and that is south. Now v4 we don't need to calculate. It's nice. There's no trigonometry involved. It's completely down, so there is no x component. You can write v4x equals 0, and the y component, v4y, is just 15 meters per second south. Okay, so now that we've found the components for each one, our next step is to add up all the x components. If we add up all the x component, remember that's going to give us the x component for the vector that is added up, which we call our resultant vector, the sum of all the other vectors. So we'll call that Rx. And then we are going to do the same thing for y. Add up all the y components, and this becomes the vertical component for our resultant vector, the sum of all the other vectors. So let's add those up. So if we're looking at our totals, we do have to remember, here we have east, west, west. Okay. Well, remember, if we're going to add east, west, west, we should make west negative east. And we should write 9.8. I should write Rx is 9.8. This is west, so minus 19.7. This is west as well, so minus 2.5. And if we do that, we get minus 12.4 meters per second. Now everything is in terms of east, but what we can do is say minus east is the same as positive 12.4 meters per second west. So we know what our x component is. Do the same for y. So for y, we have 6.9 north, and then we have 3.5 north, and 4.3 south, and 15.3 south. So these two we're going to change to negative, because we'll make north positive. So we're going to get 6.9 plus 3.5 minus 4.3 minus 15. And when we do that, we're going to get minus 8.9 meters per second. That is north. But we can change that negative north to positive south. So we have positive 8.9 meters per second south. So now we have our x and y components of our resultant. Next step. Draw your right angle triangle. So what we're pretty much doing right now is we will be drawing this right angle triangle for our resultant vector, where we know the y component and we know the x component. Okay, and then we're going to solve for that hypotenuse using the Pythagorean theorem. So let me do this on the side, nice and big. So our x component is to the west, so we have some value to the x. Whoops, that's still on laser, need pen. Some value there, that's going to be Rx. And if we add the y component, so we add the tip of x to the tail of y, which is going south, like that, that's Ry. Then our resultant vector is going to go from the tail, so our starting point, to the tip of our next vector, the ending point. So this is the vector we're looking for, which is v total. Now we know what Rx is. It has a magnitude of 12.4 meters per second, and we know what Ry is. It has a magnitude of 8.9 meters per second, and of course your x and y coordinates are at 90 degrees to each other. So if we want to find the magnitude for r, we're going to use Pythagorean theorem. So a squared plus b squared equals c squared, which gives us, take the square root of 12.4 squared plus 8.9 squared. Notice that I don't have negatives here anymore. The negative really showed me the direction. The magnitude can't be negative because that doesn't make sense. You're saying the length of something is negative. So I don't have the negatives for magnitudes. Here I should write, though, west and south. Okay, but our magnitude, you punch down your calculator, you're going to get 15.3 meters per second. Now to figure out the angle, You want to find the angle from the tail. So this angle, not this angle. That's where the tip is. Find it relative to the tail so we know what direction it is pointing to. That's the theta we want to look for. And that's going to be our final step. If you look here, to find the direction of r, solve for the angle between the x-axis and the hypotenuse using your trig ratio. And we're going to use tan in this case. Even though we know now what all sides are, it's best to use tan because our hypotenuse was calculated with these two sides, so you're just introducing more error if you were to then use that calculated value. So I'm going to do it up here where I have some more space. And I'll write the tan of theta. Tan is opposite over adjacent, so SOHCAHTOA, opposite over adjacent. So it's 12.4 divided by 8.9. And then if you take the inverse tan of both sides and figure out what theta is, you'll get theta to be, where's my calculator? My screen just turned off. Alright, sorry. Yeah, so this is opposite over adjacent. I said it right, but I wrote it down wrong. This would be, it's a smaller thing. Opposite is 8.9 over 12.4 adjacent. Thanks for pointing that out. So when you solve for theta, you will get 36 degrees. So then you can finally state, after all this work, adding 4 vectors in 2 dimensions, we can say our resultant, or V total, is 15.3 meters per second. And then your direction goes in your square brackets. This is west, 36 degrees,